This next model is called quantity discount model. One of the assumptions that we made for the two previous models were that there is no quantity discount. That means that no matter how large of a purchase a customer have, it doesn't reduce the price. But this is not really the case in reality. So what we're going to do here, we're going to extend the first model that they actually had to purchase from the third party. They didn't produce themselves. But considering that they can have the quantity discount, that means that if they buy in large quantity, they're going to get a discount. So this is called the quantity discount model. What we want to do is we want to find the optimal quantity to order, so that our total cost of inventory, which includes the carrying cost, the ordering cost, and the purchasing cost, would be minimized. So let's see how this would work. We're going to write the formula, and based on the formula, we're going to minimize the total cost and then solve for Q, which is the optimal quantity to order. The carrying cost is similar to what we had before. That would be the quantity that the average quantity in the inventory, or the quantity that you order. So that would be Q plus 0 divided by 2, half of Q. So that would give you the average quantity in the inventory. If you multiply that by H, which is the carrying cost per unit, that's going to give you the carrying cost of the inventory. The next component is the ordering cost. So this is also similar to what we had before. The ordering cost is how many times you put an order multiplied by the ordering cost per unit, which is per order, which is S here. So the number of times that you would order if you order Q each time, that would be demand divided by the quantity that you order. So that's D divided by Q multiplied by S. So this would give us the ordering cost. The next component is the purchasing cost. So this is where the quantity discount would apply. So that's equal to P multiplied by D. P is the price unit price, and D is the demand. That's how many actually you would order. Let's see how the new model works. So let's take a look back at the model. So the total cost for the quantity discount model has three components. The first two components are exactly the same as the components of the first model. So that's the carrying cost, which is half of Q multiplied by H, plus the ordering cost, which is how many times we order, which is D divided by Q multiplied by S, plus the last component. The last component is the cost component for purchase cost. The purchase cost is price multiplied by how many you order cumulatively. So in a whole year, we're gonna have to order as much as the demand. So that's going to be demand multiplied by the amount of demand multiplied by the price. So this last component is just the purchasing cost. But this wouldn't really, the purchase cost also was part of the total cost in the first model, but it wouldn't affect the total cost, the quantity, optimal quantity to order. How? Let's see how. So if you do not consider the purchase cost, that means the first model that we have, this would be the plot, the graph. So that's the total cost without the PD component, the purchase component. But if we actually had added the purchase component to the first model, because the first model, one of the assumption was that we don't have discount model. That means that the price would be the same no matter how much you actually order. So it's irrelevant of the amount of order. So the purchase component would be a line like this. It would be constant. the price would be constant. So what's going to happen if we have added this component to our first model, it would actually equally, every point, it would equally shift to the above. So we would get this model, which as you see here, the shape is the same, it just have shifted upward. And in both of these, the minimum the quantity that would gives us the minimum cost, this is cost on the y-axis, the quantity to order to minimize the cost would occur at this point here, as you see here, which is similar to this point. The quantity would be the same. So including or excluding the purchase cost in the first model would not make any difference for computing the optimal quantity, which is EOQ. It would be the same. The optimal quantity would stay the same. So that's why we actually didn't include it in the first model to find when we were trying to find the optimal quantity to order. But when we have the discount model, the price component would be different. So for example, suppose that we have 3 different prices. If you order this much, you're gonna get this price. If you order between these two, you're gonna get this price. And if you order more than that, you're gonna get this price. So the PD line, as you see here, is different. This means that considering the PD, the total cost plot or graph would be actually different in different shape than you see it here. So that's why when the price changes, that means that when you have discount discount in your system, which is a reality, you can have quantity discount when you order in bulk larger. So you need to include the purchasing cost, this line that I just had it, so that you could find the optimal quantity. The optimal quantity would be different. It wouldn't be this point necessarily, not necessarily would be this point. So let's see how it works. Still the total cost curve when you consider the discounts price component. So if you have discounts, suppose that less than $45, if you buy less than 45 and 45, you're going to get a price of $2. So the purchase component would be this price multiplied by demand. So that would be this line. So the purchase cost would be this much. And it says that if you buy between 45 and 70, you're going to get a price discount of 30 cents, which is going to get you a price of 1.7. So at 1.7, this is going to be your purchase cost. And it says that if you buy more than 70, you're going to get a discount of 60 cents. So your purchase cost would be $1.40 and your purchase cost would be this line. So now we have 3 different purchase costs here based on the demand and quantity. And that's going to impact the total cost. So this means that if you buy between 45, less than 45, this is going to be your total cost curve. If you buy between 45 and 70, this is going to be your total curve. The curve of total cost. If you buy more than 70, then this is going to be your curve for total cost. So now what we are looking for is the minimum, the quantity that would minimize the price. So this is visual. This is a graph. So it's easy actually to find the minimum of this graph. What you need to do is just look at these 3 parts of the graph and find a point which on this axis, which is the cost axis, would have the minimum cost. So this means that somewhere here it would be, which is this point. So this point would be our minimum. That means that the optimal quantity would be 70. So this is easy to find because it's visual. But what if it's not, if it wasn't visual? What if you didn't have to, you didn't want to actually plot this before you could find the optimal quantity? So let's see what is the procedure for that? What process should we use? The procedure for determining the overall economic order quantity differs slightly based on whether the carrying cost is stated as a constant or as a percentage of unit price. So there's going to be two scenarios. Let's start the first scenario now. Let's study the first scenario. The first scenario is that the carrying cost, assume that the carrying cost is considered as a constant. So H is constant here. If H is constant, this is the procedure to find the optimal quantity, economic quantity. One, start with computing the common minimum point. So you're gonna find the quantity point here, which is using the formula that would be square root of 2 multiplied by D multiplied by S divided by H. So this is gonna give you a quantity. But only one of the unit prices, because you're going to have different price ranges for different quantities, because this is a discount model. Only one of the unit prices will have the minimum point in its feasible range. Since the ranges do not overlap, identify the range that has that minimum point. This is how we do it. A, if the feasible minimum point is on the lowest price range, that is the optimal order quantity. So if this Q belongs to a price range which is the lowest, that is going to be your optimal quantity. If it's not, move on to part B. Part B says that compute the total cost for the minimum point and for the price breaks of all lower unit costs. So you need to consider the quantity that you find, the price range for this quantity that you find, and also for any price lower than that, you need to find the minimum point for those price ranges as well. And then compare the total cost uh, of inventory, that's the carrying cost plus the order cost plus the purchasing cost, and the quantity that would give you the lowest total cost, that would be your optimal order quantity. So let's go ahead and do an example. Solve an example actually would help you to understand this better. Let's do example. The maintenance department of a large hospital uses about 816 cases of liquid cleanser annually. Ordering costs are $12. Carrying costs are $4 per case per year. And the new price schedule indicates that orders of less than 50 cases, it costs $20 per case. If they purchase between 50 to 79, they're gonna get a discount of $2, so the price would be $18 per case. If they order between 80 and 99, they're gonna get another $1 discount, and the purchase price would be $17 per case. And if they purchase more than 99, which is $100 and more, they're gonna get another discount, and the purchase price would be $16 per case. Determine the optimal order quantity and the total cost. So please hold on, pause, and work on the problem. Try to solve the problem, and after you are done, come back to see the solution. Let's solve this example. So the annual demand is for this hospital is 816 cases. The holding cost per case per year is $4. And the ordering cost per order is $12. This is a discount model. That means that based on their order amount, they're going to get different prices. So the problem says that if they order less than 50, so if the quantity that they order is less than 50, which is less than equal to 49, the price that they're going to get is $20. If they order between 50 and 79, so if they order between 79 and 50, the price that they're going to get is with $2 discounts at $18 per case. If they order between 80 and 99, you're going to get another discount and the price would be $17. And if they order more than 100 and more, they're going to get another discount and the price would be $16. So now let's find the optimal quantity. So we start off by using the formula here to find the general optimal quantity. So that would be Q equal to a square root of 2 multiplied by D, which is 816, multiplied by S, which is 12, divided by 4. And that's going to be 69.97. If we round this up, it would be 70. So the quantity that we find using this formula is 70. Now we need to check whether this quantity is at the lowest price range. Is it? The lowest price range is $16 and for quantities greater than 100. This quantity is not at the lowest price range. It's not even at the second price range, lowest price range. For that, it needs to be between 80 and 99. This quantity is actually at the third price range here at $18. So this means that we need to find also the quantity for the lowest two price for $17 and for $16, and we find the total cost for those and then compare them to each other. Whichever quantity gives us the lowest cost is the smallest, then that quantity would be our optimal quantity. So this means that we're going to have to find the total cost when we order at 70. We're going to have to find the total cost when we order at the first price range, the lowest price range, which is 16. So the smallest quantity is 100. So we're going to find the total cost when we order 100. And we need to find also the total cost for the second price range, which is at $17, and the minimal quantity would be 80. So we're going to find also the total cost when the quantity is 80. All right, so let's go with the first one, the total cost when we order 70. If we order 70 using this formula, total cost formula here, the total cost would be Q divided by 2 multiplied by H. So that's 70 divided by 2 multiplied by H, which is 4, plus D multiplied by S divided by Q. So that's the second part down here. I'm going to write it here as D That's 816 multiplied by 12 divided by Q, which is 70, plus the third component, which is price multiplied by demand. So that's P multiplied by D here. The price is 18 multiplied by D. So that's 18 multiplied by demand, which is 816. So if you do this math, the total cost will be 14,968. So I'm going to clear this up. 14,968. $68. Next, we're going to find the total cost for the quantity that we ordered, 80. So if you do that using this formula, which is going to be Q divided by 2, so that's 80 divided by 2, which is 40. 40 multiplied by H, which is 4, plus D divided by Q, so that's 816 divided by 80 multiplied by S, which is 12, plus PD. So PD is price for 80 is here is 17. So that's 17 multiplied by demand, which is 816. So if you do this math, this is going to be $14,154. $14,154. So I'm going to write it here. And I'm going to clear this up. Oh, we have to do it here. So that would be 14,154. So that's and then we're going to compute this for when we order Q equal to 100. Q equal to 100, the price is $16. So we're going to put it in this formula down here and we find the total cost. So that would be Q divided by 2. So that's 100 divided by 2. 100 divided by 2 multiplied by H, which is 4, plus D divided by Q. So that's 816 divided by 100 multiplied by S, which is 12, plus P multiplied by D. P here is 16. So that's 16 multiplied by 816. So if you do the math, this would be equal to 13,354. So that's 13,354. So as you see here, the amount between these three, the minimum is 13,354, which is for quantity equal to 100. So this means that the optimal quantity which would make our total cost minimum is 100. So they need to order at a size of 100 here. All right, so this is a neater and cleaner version of the solution method. We also have a graph of the total cost for this problem at different prices as you see here. So if they order less than 50, this would be the total cost. If they order between 50 and 70, this would be the total cost curve. Between 50 and 79, so this would be. If they order between 80 and 99, so this would be their total cost. And if they order more than 100, this would be their total cost. So if you look at actually this, because you want to, you have to look at the total cost on the y-axis. So if you can look at this, you're going to see the smallest one that has the total cost would be actually this right here, which would occur at the price at the quantity of 100. Because this is visual, but you don't have, we didn't want to plot actually this. Plotting this wouldn't be easy if you want to do it by hand. So the way to do this is going through the step that we went through. We need to find the common minimum point. So this is the common minimum point here. Optimal quantity, that's 70 cases. If you look at 70 cases here, 70, this is not as the lowest price range. So we need to compare that to the two lower ranges here. That's what we did. We computed the total cost for this range and for this range, which would occur at the minimum point of 80 for this one and 100 for this one. So we computed the total cost when the quantity is 70 and we get 14,968. But we also need to compute the total cost for the lower range prices at 17 and 16. At 17, the quantity is at least 80. So the total cost we computed that was 14,154. For the price range of 16, the minimum quantity is 100. So we need to compute the total cost when you order 100, and that we computed that was $13,354, which is between these three is the minimum price, the minimum cost. So this means that 100, this quantity that we have here, 100, this would be our optimal quantity to order. That would minimize our total cost.